Welcome back. I hope you've managed to recap all of those probability rules and terms that we've gone over. And I hope it's making some sense. I hope you remember some of those from work that you've done possibly in a previous year or in a previous lesson. So make sure that you're very familiar with these particular terms. They are very important. We ended off by talking about mutually exclusive events. We recognize those are events that do not have an intersection. For example, when you spin a coin and you toss a coin, we know that it can either land on a head or a tail. So it can't land between a head or a tail. So the number of times that it lands on heads or the number of times it lands on tails, those are mutually exclusive. It can't land on a head and a tail. There's no intersection. It can't be half of one and half of the other. And so please make sure that you understand that. But there are events that can take place when two things can be in common. So something can belong to two sets or two events that make sense, that overlap. Okay, we're going to look at such an example just now when we have a look at a particular game of rolling a dice. In fact, we're going to roll two dice, but let's get into the idea that we're talking about. So for mutually exclusive events, we recognize that the probability of P or Y is equal to the probability of X plus Y. That is for mutually exclusive. What we want to ask the question, does this hold true if the events are not mutually exclusive? We know this is true if they are mutually exclusive. If they are mutually exclusive, there's no intersection, and we recognize that we can take the probability of the individuals and add them together, and we'll get the intersection of the P, X, or Y. Okay? Please remember that when we talk about P of X or Y, we're not talking about a smaller set. We're actually talking about a bigger set. The conditions are less stringent. It isn't just P, but the element can be in P or it can be in Y. So there are more options. You've got to be very clear about this. People often think that all means it's a smaller group. It's not. It's a less of a condition. It can be P of X or in Y. So please make that very clear, particularly when we come to talk about intersection, when we're going to be using the word and. And now you might think it becomes bigger, but actually it becomes smaller. And so that's a little bit of the thing that you're going to have to get your mind around, and we'll mention it again. So, does this hold true for mutually exclusive events? Well, let's have a look at our game. So let S be the sample space of numbers on a die, and we've got two die, because we're going to have a game of rolling two die, and a die X will produce blue numbers, and die Z will produce red numbers. So let's just think about that for a minute. The red numbers on the red die, there can be 6 of them. That would be in the sample space. And in the blue numbers, there would be 6 of them. So the total number of elements in the sample space is 12. That's right, there are 12 numbers in the sample space. And we can represent that like this. In our diagram, we can see we've got numbers 1 to 6, blue, and 1 to 6 in the red zone. Now, what are the rules of the game? Remember, the game is all about winning, and there are only certain things that are going to make you a winner. Very important that you understand the rules, because you're going to take turns, and you're going to throw 2 dice, and you want to know whether you've won the round or not. So, have a look at what the rules are for this particular game. The winner of a round rolls die X with a value that is greater than 2. These belong to set X. So when we think about this, not all the numbers that are part of the X are going to be winning numbers. Only some of them. They have to be greater than 2. So that means it can't be 1, it can't be 2. But if it's greater than 2, then it will be 3, 4, 5, and 6. So there are 4 numbers that will be true for making you a winner. That will be set X. There we go. We've got 3, 4, 5, and 6. Very good. I hope you understand that it's those ones that we're looking at. So we've calculated and we've seen graphically that there are 4 possibilities for winning when rolling dice X. But what about the second dice? What about dice Z? Have a look what the rules are. So in this game, dice Z, you can be a winner with a value that is less than 4. And these have to belong to set Z. So it's not the same as it was for dice X. Dice Z, the red dice, now has a different set of criteria that make you a winner. Have a look at it in the graphic form. Here we go. There's all our values. And what we recognize is that there are 3 values that you can win with slide or set Z. If you roll a 1, 3, or 2, you can be a winner with slide Z. Do you notice something? What's the total number of values that are either in set X or in set Z? That's an interesting question. Remember our OR rule. That means union. They must be either in X or Z. Let's have a look. We're going to say that we notice that there were 7 values altogether, but there's an intersection. 3 is common to both X and Z. There's only one element. So we can say immediately, we know that there's an intersection, they're not mutually exclusive. So of the 7 values, now remember what I've said, when there is an overlap, we're not going to count the red 3 and the blue 3 as separate values. No, they're intersecting. They just have one value. So we're only going to count those once. We must make sure that's true. And so when we do this, we're going to say to ourselves, in how many ways can we win rolling dice X? And what is the probability of rolling a winning number with dice X? Well, let's have a look at the picture again. So there we go. We've got the number of winning numbers, the number in X, and I think we can show X over there. We can say there are 4. The number in X is going to be 4. And what's the probability? Well, the probability of winning here is we know that there are a total of the probability of X is going to be the total of the number in X divided by the number in the sample space. And if we do that, we'll recognize that is going to be a value of 4 out of 12. Okay, let's see if we've got that. And we move on and we say to ourselves, in how many ways can you win rolling dice Z? Well, that's not that difficult. And we can count it. If we look at the Venn diagram is very useful for us to see exactly what's happening. So count with me. If we go to our slide Z or our set Z, we recognize the number in Z this time is only going to be 3 values, 1, 2, and 3. So there are 3 values. So the probability is going to be, the probability of Z is going to be the total number of z, which is 3, divided by the total number of values in the set. So we're going to get a value of 3 out of 12. Not quite the same, because you'll recognize there were more in x, less in z. Now there's a problem, because what we recognize is if we were to look at the union of those two, in other words, if it was in x or z, then what's that number going to be? Let's have a look at the question. What happens if a dice falls on 3? Does it matter which die falls on 3? No, it doesn't matter. We recognize 3 will still be a winning number. So the number of times that we can... So 3 is a winner. But we're just going to count the 3 once, because it's in the intersection. Now, if we look at how many times you can you can win rolling dice X or Z, this is what I wanted to get to. We recognize how many ways you can win in X or Z. So we recognize, Right, what's the number that we can find in the union of X union Z? Now remember, these are all the values that are going to make you a winner. So we can count all of those numbers, and we will find that there are 6 values. Because remember what we've just said, that in the intersection, we're only going to count 3 once, because in the intersection, the 3 belongs to X and to Z. But if we're looking at the union, we're going to look at only 1 value in the intersection. So there are 6 possible ways of winning. So what's the probability? Well, it's not difficult to work out. The probability of X union Z is going to be the number of X union Z, which is 6, divided by 12. Now, if you look at that, that's an interesting result. Very interesting, because if you remember what we've calculated earlier, it kind of breaks down a little bit of a rule. But let's have a look. So if you look here, you'll recognize that we've only got 6 numbers in this union. And so that's why I've indicated this as the union of X and Z. There are 6 numbers, and you can see them very clearly. This one is in the intersection. And when we do the calculation of the probability, we have to ask ourselves then is what is that probability? And we've calculated it already. Jumped ahead a little bit. We've said that that probability is going to be 6 out of 12. But do you remember we calculated earlier that the probability of X was 4 out of 12, and the probability of Z was only 3 out of 12. So guys, that kind of doesn't add up, does it? We've got a little bit of a problem here. And so remember, this is clearly indicating that these 2 sets are not mutually exclusive. Because if they were mutually exclusive, then the OR rule would apply. We'd be able to take the probability of X plus the probability of Z, and it would add up to the probability of X or Z. But that's not the case. So let's be very clear. Is the identity for union true? And the answer is definitely no. It is not true. We've shown you the values. So what conclusions can we make? How can we make it? What is the thing that is breaking the rule here? Well, it's that idea of dealing with what's in the intersection. You see, 3 belongs to both x as well as belonging to z. And we can't count it twice. When we count the probability of x and then we count the probability of z, we're counting the 3 in both of those. And we're not taking into account that it's in the intersection. So when we have sets that are not mutually exclusive, we've actually got to take away the amount in the intersection, so to avoid the double counting. So in this respect, we can have a look and we can see that if you do that, you recognize there's only one value that's representing 2. We've got to take away the amount in the intersection. And so as I've got it here, you can recognize that this was 6 out of 12, this was 4 out of 12, this was 3 out of 12, and in the intersection we've got 1 out of 12. Now if you add these two together, you get 7 out of 12, and can you see there's 1 out of 12 here? So what happens if I subtracted that 1 out of 12? Well, then it could get to be 6 out of 12. And that's exactly what we're going to do. When we have sets that do have an overlap, that do have an intersection, where the intersection is not 0. In other words, for non-exclusive sets, non-mutually exclusive sets, sets that are not mutually exclusive, we can have this identity. And we're going to use this as our OR rule for things that are not mutually exclusive. Take a note what we do. We say it's P, the probability of x or z, is equal to the probability of P of x plus P of z minus what's in the intersection. And that, boys and girls, ladies and gentlemen, is the most important rule for calculating the OR symbol. Okay, so please remember there are 2, one for mutually exclusive and one's when the mutually exclusive rule doesn't apply. They are really the same thing, because when we have mutually exclusive, then the intersection is 0. I know that's given you a lot of food for thought. I hope you're going to practice this. And I'm going to give you the opportunity to practice all these rules. But first, let's take a quick break.